One more thing that we will see, not so extensively at the beginning, but later on, is a notion of a transform of a system. Okay? So again, the system is represented this way. These are time sequences, right? And so, you know, we said that the system is represented in terms of a convolution kernel over here. All of that stuff we've seen. Now, one way to represent the convolution kernel is to take a transform of this kernel. Okay? This transform is written exactly this way. And Q, by the way, in this expression, okay, is a complex variable, okay? So Q over here is what we call C, which is the class of complex variables. It can be different interpretations for this, but I like the interpretation that you plug in a Q that is a complex number. So what you're doing is you're mapping h of k to a complex valued function. Of complex variables. That is, itself becomes complex and it acts on a complex quantity. So we go from a time sequence into this function of complex variables. Functions of complex variables are very interesting in many different ways. For those of you who might have studied those in school or in college, you know that they have properties of analyticity and so forth. I mean, there's a lot of interesting stuff that we know about these types of functions, and they are important in the characterization of linear system theory. We won't delve too deep into the complex theory over here, but once in a while, we will appeal to some of these results because they're actually powerful in terms of the type of representations we like. There are different notations that you see. Engineers in general would use Z instead of Q. Mathematicians use lambda instead of Q. And a lot of communities in system identification and learning use Q. This is the same type of a transform. We in engineering used to call it the Z transform. The Gelfand transform in mathematics is typically used with a lambda notation. So if you've seen this before in a different form or a different transform, it's the same thing. Okay. Now, one thing that is actually quite interesting about this is that, well, okay, so let's just kind of take an example. I like the discrete integration example because it's a very simple example. Remember, h of k here is just equal to 1 for k greater than or equal to 0. So what would be the Q transform of this? We just plug it in. So h of q in this case is going to be just a summation from k equals minus infinity to infinity, h of k q to the minus power k. But this would just be the same as k equals 0 to infinity, and h of k would be 1 at that point. So it's just a summation from k equals 0 to infinity, q to the minus k. Okay. Now, this is a complex variable quantity. It's an infinite series. It can be computed, this integral, right, this summation, and this summation will be equal to, if you just think of it as a dummy variable, q as a dummy variable, it will be 1 over 1 minus q. Okay. 1 over 1 minus q. But actually, this summation is well defined only when the amplitude of q is greater than 1. Okay, so only when the amplitude of q is greater than 1. Okay, actually, it's q minus q inverse, sorry. Yeah. Okay, so when the amplitude of q is greater than 1, this summation is well defined, because when amplitude of q is greater than 1, this quantity is actually a decaying exponential, and so the summation is finite. If the amplitude of q is less than 1, this is a growing exponential and it's not defined. This quantity over here, okay, it's called the region of convergence, okay, for the complex valued function h of q. Again, this is a little bit too much information here, but the point is that when we define h of q, it's not always that it's defined for every variable q, because it may not be summable for every variable of q. As you have learned, infinite series don't always converge. So you can't always write the summation, but there will be a region of convergence. And no matter what complicated function you really give me, there's always a space in the complex plane where the summation will be defined, roughly speaking. Okay. So that's how we compute the transform. Why do I care about this? I'm going to show you in not too long, in the next module, that in fact, this is a very quick way of thinking about linear systems. And an interpretation of that comes as the Fourier transform and how we think of linear systems in terms of frequencies. Okay, so that's an intuitive thinking about linear systems that also plays a critical role in understanding of what's going on there. The one thing I want to say without proof right now, but we will have an opportunity to think about this a little bit more, is that the Q transform also relate to the notion of stability in a quick way. That is, the system is bounded input, bounded output stable. And I'm not writing this as an exact theorem because it can be a little tricky, but in principle or in sort of in a sense of approximation, what you need to do is look at the poles of H of Q. Remember, H of Q is a function of complex variables. So it has zeros and poles. So we think of H of Q typically as a numerator as a function of Q and over a denominator as a function of Q. And what you need to do is to look at the pole, at the zeros of the denominator, and make sure that these zeros are outside the unit disk. Their magnitude is greater than 1. Okay? That's, again, a characterization of stability that allows us to automatically look at the transform and say whether the actual system that we're looking at is stable or not. There will be some examples in the future that we look at. I'm not going to emphasize this yet, but when we talk about representations of stochastic processes, we will have to appeal to this because we need a notion of stability and we need a characterization of the notion of stability. Okay? So for now, we define a transform on a linear system. The transform really is mapping a convolution kernel, which is a function of time, to a complex valued function of complex variables. And we are promising that this is going to actually help us understand more intuitively what a linear system is.